Welcome back to linear algebra. In this video, we're going to look at some more properties of matrices. So without further ado, let me get my head out of the way and let's dive right in. Remember from our previous discussion, that any n by n matrix, any matrix that has the same number of rows and columns, is called a square matrix. And when you have a square matrix, we can talk about the main diagonal of the matrix as the A sub II entries. If you think about what a square matrix might look like, the main diagonal, that doesn't really show well enough. Let's try this instead. The main diagonal of the square matrix are the entries along this line. And so with those two ideas alone, a natural extension is the idea of a diagonal matrix. A diagonal matrix is a square matrix for which each entry which is not on the main diagonal is 0. I want to point out a distinction between a diagonal matrix and the reduced row echelon form we've talked about previously. Reduced row echelon form in a perfect world, in a invertible matrix, will be a diagonal matrix where every entry on the diagonal is 1. The thing to pay attention to about a diagonal matrix generalized is that we say absolutely nothing about what is on the main diagonal. It could in fact be that every entry on the main diagonal is also 0. So really boring matrix, the 0 matrix, but it is still a diagonal matrix. More to the point and more interestingly, as we'll see in the very near future, diagonal matrices where some of the entries are 0 are going to have a lot of very interesting properties that are going to turn out to be useful to us. Diagonal matrices where none of the entries are 0 are also going to have some interesting properties. Diagonal matrices where all of the entries are 0, very boring. Diagonal matrices where all of the entries are the same, also kind of boring. So I want to work with diagonal matrices today. in order to do that, we have to go back and think about a couple of other things we can do with matrices in general. The first thing we can do is handle exponents on matrices. This is supposed to be a k, that just really doesn't look like one. The a raised to the k power, just like exponents on numbers, means multiply that matrix by itself k times. And I do want to stress in this definition that we can only do this when A is a square matrix. If A is not a square matrix, then multiplying a matrix by itself probably isn't defined in the first place. Let's move that down so I have a little bit more space to work around it. Let's consider an diagonal matrix. I'll call the diagonal matrix capital D for diagonal. And you'll see that I named the entries on the main diagonal with the Greek letter lowercase lambda. Drawn a little bit bigger there if you're not familiar with it. The reason we use lambda is going to be useful to us much later in the course, but for now, just a convenient notation. We'll call the entries on the diagonal of a diagonal matrix using the Greek letter lambda instead of having to use the double subscript that normally we use in a matrix. But those entries might not be zero, they might be zero. All the other entries definitely are zero. And I don't quite have enough room to put the diagonal matrix and the theorem on the screen at the same time, I don't think. But I have a nice theorem about diagonal matrices, which says that diagonal matrix D raised to the n power literally takes not n power, k power. I already used n to mean something else. Diagonal matrix D raised to the k power literally takes each of the entries on that main diagonal and raises them to that power. All the other entries remain zero, so you still have a diagonal matrix. For the sake of time, I'm not going to try to prove this happens in general, but instead, let's take a look at a particular diagonal matrix. This is a 3 by 3 matrix with diagonal entries of 2, 3, and 5. Everything else is 0. And let's go ahead and raise that to the third power. Well, if we start off multiplying two copies of this matrix together, you can see pretty quickly why, in general, if you multiply two diagonal matrices together, the result will be diagonal because we dot row with column, and we've got a bunch of zeros and a bunch of zeros that don't really do anything, leaving us just with 2 times 2, which is 4. First row and second column, everything gets multiplied by a 0 one way or the other. Likewise, most of these, except for the entries on the diagonal, which very conveniently end up exactly those powers. And then, because we said we wanted a third power, we take the matrix we got as the result here and simply multiply again by our starting matrix. To get that resulting matrix, that's exactly what the theorem predicted. 800, 0270, 00, 125. One of the things I love about this theorem if each lambda k is non-zero, if each of the entries on the diagonal of this diagonal matrix are not zero, then the matrix we have is invertible and the inverse matrix can be found very simply by taking the reciprocal of each of the main diagonal entries. Again, for the sake of time, I'm not going to prove that corollary. It's a very interesting result. But let's take a look at a specific matrix here. Actually, let's take a look at the same matrix we were just looking at. Two zero zero, 030, 005. And let's multiply by the matrix that this corollary predicts will be the inverse matrix. 1 over 2, 0, 0, 0, 1 over 3, 0, 0, 0, 1 over 5. Work through the matrix multiplication row times column and recognize that we do in fact get the 3 by 3 identity matrix as the result here. Right? So not a proof, but a nice illustration that this corollary is going to hold for us. generalizing the idea of a diagonal matrix a little bit, we have the triangular matrices. There are two kinds of triangular matrix. We're going to not worry too much about the distinction between them. An upper triangular matrix has all entries which are below the main diagonal 0. A lower triangular matrix has all entries which are above the main diagonal 0. And the way that the definitions of triangular matrices are typically presented feels a little bit backwards. So we have to take a couple of minutes and think about what we're really saying about a triangular matrix to make these properties actually make sense. In an upper triangular matrix, consider here a matrix of arbitrary size with the main diagonal looking something like that. In an upper triangular matrix, all of the entries below that diagonal are 0. All of the entries on the diagonal or above the diagonal could be non-zero. So what you end up with is this triangle of interesting things in the top part of the matrix and a whole bunch of zeros in the bottom part of the matrix. And the lower triangular matrix just flips that discussion. In a lower triangular matrix, we have a main diagonal, we have a triangle of potentially interesting things on and below the main diagonal, and a bunch of zeros above the main diagonal. Zeros are essentially not interesting. Non-zero bits are interesting. An interesting bit of terminology. This always bothered me when I was a student, but since I have gone beyond that point in my study and started to see more and more places where the ideas of triangular matrices are useful, I began to see why this is the case. A diagonal matrix is both an upper triangular matrix and a lower triangular matrix. Like I said, when I was a student, I always felt like triangular matrix should specifically be a thing where all these points are non-zero, not just talking about where things are 0. Because the zero matrix, the matrix where everything is 0, the most boring matrix there is still a diagonal matrix, is still an upper triangular matrix, is still a lower triangular matrix. These are weird corner cases. These are places essentially where we kind of just shrug and say, well, it's there, it works, good enough. So it is more convenient in higher level mathematics to just say that the definition of triangular matrix is as general as possible, and that just includes diagonal matrix in both forms of triangular matrix, and all the properties we can prove for triangular matrices are automatically taken by a diagonal matrices as well. Diagonal matrices will have a couple of properties that triangular matrices do not. Switching gears, I want to take a look at an operation that I mentioned briefly earlier, and that is the transpose. Remember, we denote the transpose of matrix A using a superscript T. And the transpose of matrix A switches the rows and columns. So if A is an M by N matrix with entries given as little a sub ij, then A transpose is an N by M matrix with entries given as a ji. Specifically, we will be looking here at transposes of some square matrices. I'm jumping ahead of myself, sorry. First theorem, fairly straightforward. If I take the transpose of a transpose, I get back the original matrix, which I think makes a lot of sense. If I transpose the matrix here, 2 rows, 3 columns, 1, 2, 3, 4, 5, 6, I get a matrix with 3 rows and 2 columns. One, 4, 2, 5, 3, 6. If I take the transpose of 1, 4, 2, 5, 3, 6, I will get 1, 2, 3, 4, 5, 6. Using the basic idea of the transpose operation, I think that's a fairly straightforward result. Another interesting property of the transpose operation is if you have 2 matrices you're going to be multiplying together and you transpose the product, it is the same thing as taking the transpose of each of those matrices before multiplying together. This one takes a little bit more thought to see that it makes sense. Remember, when you multiply 2 matrices, you take each row with the corresponding column. So the rows of A are the columns of A transpose, and the rows of B are the columns of B are the rows of B transpose. So if you take a row of A and a column of B, that's the same thing as taking a row of B transpose and a column of A transpose. And then taking the transpose of everything on the left-hand side is because with the transpose operation, things will end up in a slightly different order. Right? If we call this AB transpose Cij, then the entry comes from multiplying the ith row of A with the jth column of B. And if we take B transpose times A transpose and try to call that Dij, I'm sorry, I wrote down too much over here. That was just supposed to be AB is Cij. B transpose A transpose Dij. But this is coming from the ith row of B transpose, which is the ith column of B, and the jth column of A transpose, which is the jth row of A. And what you can see in looking at these two things is that we have swapped I and J between AB and B transpose A transpose. And that's what it takes to get that AB transpose equals B transpose A transpose. All right, so a couple of interesting ideas on the transpose of a matrix. Now that we have that, let's take a look at one of the several places we're going to use the transpose, and that is talking about a symmetric matrix. We say that a matrix is symmetric if and only if that matrix is equal to its own transpose. And I'm getting ahead of myself again, I apologize. A symmetric matrix is a matrix that really mirrors itself. Right? So think about an arbitrary matrix where you have specific entries on the main diagonal. And the main diagonal of the square matrix can be literally anything in this case. But the entries off of the main diagonal have a symmetry about them. If I put a 4 here, I have to put that exact same 4 there. A 5 here translates to a 5 there, and a 6 here translates to a 6 there. So that if you fold the matrix along the main diagonal, you get like entries lining up with themselves. Symmetric matrices are really useful because when you can identify a symmetric matrix, you can save yourself a lot of computational headache in trying to perform operations on matrices. So, to end up this video, I want to just talk about a couple of ways we can identify that a matrix is symmetric. The easiest one, if you have any square matrix A and you multiply matrix A times its transpose, either as A transpose times A or A times A transpose, either order, because just let B equal A transpose and then A transpose A is the same thing as B times B transpose. Either order, you get a symmetric matrix out. The proof of this theorem is very straightforward. What does it mean for a matrix to be symmetric? If you take the transpose, you get back the thing you started. So if I want to take the thing I started with, A transpose times A, and take its transpose, well, we saw that the transpose of a product is the product of the transposes, but written in the other order. So we'll have A transpose, and we'll have A transpose transpose. A transpose is just A transpose, and the transpose of a matrix is just that original matrix. So we get back to A transpose times A really that fast. The last couple of properties I'm not going to take the time to prove, but a couple of useful things that can show up in a couple of corner cases. If matrix A is both invertible and symmetric, then its inverse is going to be symmetric. And one way to think about this is using the theorem we just looked at. If you take A inverse times A, if you take A inverse times A, you are going to get the identity matrix. It stands to reason that if I take the transpose of A inverse times A, I will get the transpose of the identity matrix. And I hope that you will agree with me that the transpose of the identity matrix is just the identity matrix. On the left-hand side, I can use the theorem we just looked at. Not the theorem we just looked at, but the same theorem that we used in the last proof, to say that A inverse times A transpose is A transpose times A inverse transpose. But because A is symmetric, A transpose is the same thing as A. So A times A inverse transpose is the identity matrix. And finally, a result we mentioned but didn't prove earlier, the inverse matrix is unique. There is exactly one inverse of any matrix. And clearly, A inverse transpose is the inverse of A based on this equation. So A inverse transpose is A, which is the definition of a symmetric matrix. So A inverse is in fact symmetric as well.